All right, so let's talk about testing practices. The previous lecture talked about a lot of the terminology, what the problem is, right? Whereas this one deals with some of the practices that we use to be able to deal with the combinatorial explosion. How do we deal with that? How do we identify the actual edge cases and the representative values for a whole range of possible values that we need to consider? And what are the strategies that we might use to write these tests and execute them? So first of all, we need to identify that tests typically fall from or derive from some requirements, right? That somebody has expressed an interest on some application and described to us how it should behave. And testing is nothing but validating that the application behaves as is expected, right? As the specification describes. Now, it could be that there are no specifications, that this is might be an application that was purchased or was acquired or through maybe it's a legacy application. There's no documentation, no specification. We only have the application per se. In that case, typically the application becomes the specification. We can ad hoc randomly use the application and learn how it works and document its behavior and try to reverse engineer its behavior, and the application itself becomes the specification going forward. So that we know that it worked well under these conditions. If we're going to add new features or we're going to change something or fix something, we know that well, it used to work at some point. We don't want to introduce any new bugs. So typically we try to reverse engineer, create a specification for something that works as is, and then work forward from there. In most cases, we don't use exploratory testing, right? That's called exploratory testing. Just ad hoc explore the application, a random application, randomly explore. Most cases, it's an application that has gone through the whole entire life cycle of development, of use case analysis, of functional requirements, design and planning and whatnot, and typically these are the ones we're going to focus mostly on, and typically this would allow us to taking these functional requirements, these use case analysis. We could write the tests even before the application is even built, even before we write any single line of code. Some philosophies or some shops use this technique, often referred to as test-driven development, where the first thing that the things are developed, the first artifacts are developed are the tests themselves, right? We write all the unit tests, we write all the first, right, which basically are a formal representation of some ephemeral use case or some abstract functional requirement into some concrete test that the application needs to pass, right? And once you write this family of tests, even before you start implementing the application then becomes an exercise at passing those tests, right? Every single line of code that you write is towards passing the tests that were written at some point, right? And there's a very objective way of measuring your progress. The progress is basically, I've passed this test, meaning I have fulfilled a particular requirement that was formally implemented or concretely represented as a test. Okay. All right. So we're not getting into test-driven design just yet. Let's talk about how is it that these tests would be implemented or derived or identified in the first place. So typically writing these tests, it involves revisiting the use cases, right, and looking at the base paths, all the different actions that the user has taken, and which describes the behavior on a conversation or a dialogue between the user and the application. The user does this and the application does that. This, that, right? So basically that gives us a family of stimuli that the application should be able to respond to, right? And what the expected behavior or output of the application should be. So those scenarios, typically a use case will have multiple scenarios. We'll have the basic path, right? The happy path will be, the scenario that is more prominent. But then we'll have also all sorts of variations, right, of different other scenarios, considering of many different edge cases, handling different errors, handling different different alternatives. Those two become potential inputs or potential sources where we can derive these tests from. Right? So the use cases, these requirements, right, is what drives the implementation or the definition of these tests. Also, as I mentioned earlier, at every single layer of the life cycle, whether it's business, when you're doing business analysis or use case analysis, functional requirements, design. At each level, your responsibility is always to question the requirements, right? Not because the requirement says that this is what we're doing. That's the test I'm writing, right? It could be that while you're writing the tests, you realize that the requirements makes no sense, or that when you concretely are writing lines of code to test a requirement, you realize that they're contradictory. It says, well, no, you can't have at the same time a discount and a fee, and they cancel out. It says, and what's the point of giving for this particular set of conditions? It just makes no sense. So that is also an opportunity, right, for the developer as they are concretely implementing these tests to question, go back to question the requirements. Is this a right use case? Is this a right functional requirement? It might make no sense, and push back, right, to the project manager, to the business analyst, even all the way up to management, is saying, this makes no sense. Again, at each level, your responsibility is always to question the requirements and go back and define exactly what it is that we're building, right, without blindly just going on and implementing it. So as we're defining the test cases from the requirements, typically we'll focus on two types of tests, right, or families of tests. One of them will be those family of tests that verify the happy path, right? That on ideal conditions, does the application behave correctly? Is it doing the things that it's supposed to do correctly, right? Without trying to break it, without trying to push it too hard. Is it doing the things that we said it would do correctly? So those usually are referred to as test to pass. Does it calculate the mortgage correctly given the interest rate and the down payment and how many years? Does it come up with the correct number of monthly payments, right? So those are the test to pass. Does it correctly do that? But then there's also, there's going to be tons of things that the user is going to do that are unexpected, right? They're going to enter weird things that are negative, or things that are out of a particular range or a different format, all sorts of unexpected things, right? And we would like to be able to deal with those unexpected inputs as early as possible. We like to be able to identify those edge cases where folks are stretching the implementation of the application to its limits, so that we like to be able to see how does it behave, where does it break, right? Usually these errors are very, very hard to find, because oftentimes we are, especially if by us, because we're intimately knowledgeable of the algorithm, right? We're intimately embedded in the day-to-day implementation, that oftentimes we are just blind to many of these edge cases, right? Oftentimes it's better to just give it to somebody who has no bias, right? No interest, has no ego on whatever was written, and have them, just bang at it and try to break it, right? So maybe they don't have the same biases as you, and they might think of other things that could be tested, right? So test to fail is the family of tests that look to push the application to its breaking edge. Okay. Typically, test cases would be formally written, following a particular test case template that everybody can agree as an organization, right? And it would specify all sorts of formal things of what are going to be the specific steps that are going to be used to test and verify that what you built is correct. Typically link it to certain functional requirements or link it to a particular use case from where these cases are derived from. Typically, a particular naming convention is used to identify, perhaps a particular phase of the project, a particular phase of the of delivery, and so that you can keep track of this family of documentation of all these tests. When was the last executed? Who executed it? What were test conditions? What version? What configuration? What browser? What version of the operating system? And all those kinds of things. So there are several strategies of writing these test cases. The ones we've already talked about is use case analysis, right? You start from use cases, you derive the different steps, and from there you can derive many test cases. But there's quite a few other strategies on how we could write tests. One of them is equivalence class partitioning. So equivalence class partitioning is trying to identify what are some representative values, right, that we can use that represent a whole range of values, right? Out of the million possible combinations that you could have of different inputs for different fields, right? What could we which values could we choose that represent an infinite range, right? If I say that numbers it's a day of the week, then obviously the range has to be Monday through Sunday, right? Or if it's numerical, maybe it's between 1 and 7, right? So the logical understanding of what the input might be immediately gives me a reduced subset of what values I might want to consider, right? And it says, okay, well, anything outside of 1 through 7 is invalid, and anything between 1 and 7 is valid. So equivalence class partitioning is the strategy of identifying which are these ranges that we can identify a particular value that can represent all the other numbers in that particular range. So for instance, 3 is a valid value that represents all the values between 1 and 7. It's a valid value. If you look at value 8 and above, 8 represents all the invalid values, right? That might represent between 8 and infinity. Or if you have all the negative numbers, any negative number might represent 0, or negative numbers might represent all the invalid values from 0 all the way down to minus infinity. Yes? So equivalence class partitioning is a strategy for reducing a potentially infinite number of things that we need to test to a more manageable subset of tests that we can still feel confident that we're testing everything. Yes? The other is boundary value analysis. That's another strategy, is that oftentimes as developers, we tend to make errors or mistakes near the boundaries of these equivalence classes, right? We oftentimes make a mistake, when we read something or we misinterpret it, and we're not sure if we have to, we're writing a loop, and we're not quite sure if we have to start at 0 or 1, or do we have to iterate till the value or the value minus 1, right? And all these edge cases of did I iterate 1 too many times or 1 too little times, right? We typically have those kinds of problems, these boundary issues, right? So boundary value analysis is the strategy of focusing on those boundaries, identifying what those boundaries are, and then writing tests that test the algorithm at those edges, right? Maybe 1 less at the value and 1 more, right? See if we can identify, make sure that it does the right thing before, at, and later, right, of those boundaries, right? So we'll talk about that. The other one is decision table. So these two, equivalence class partitioning and boundary value analysis, often involves writing nice graphs or equations or lines that draw these boundaries of what's valid, what's invalid. But oftentimes there might be too many values, right? That we might need to represent in 3-dimensional or 4-dimensional or n-dimensional space that might not be easily representable, and oftentimes that space might not be contiguous. You might have pockets of values here and pockets of values over there, which is not easily representable graphically and whatnot. So, or you might have all sorts of rules, business rules that are not easily representable by a graph or an equation. And decision tables might be a better way to capture combinatorial options that might need to be considered collectively. And finally, state charting is yet another strategy of identifying these test cases by using finite state machines and diagramming them, as we can see as applications evolve over multiple states, as they go from one mode to another mode, and different rules might apply in these different modes, identifying what test cases might be written for a particular set of inputs in a particular mode, and a different set of test cases for a different set of inputs for a different set of mode. Make sense? All right. Yeah, so the first one we already talked about is use case analysis, right? Which is basically look at the use cases, the derive, and derive from them depending on taking all the different scenarios and write test cases for each one of those scenarios. Let's take a look at equivalence classes next.